What we would like to do, we haven't done this yet, is listen in for the molecules that they emit and determine, do you have those harmful species?
Welcome to Nano Matters, the podcast that explores specific examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office, and here with me today is Paul Weiss, Distinguished Professor of Chemistry and Biochemistry, Bioengineering, and Material Science and Engineering at UCLA. Paul is an expert in a fabrication technique called Nanolithography. So, Paul, what is nanolithography and how does it work?
Well, the way conventional, we'll call it nanolithography, works is really a direct descendant of stone and wood carving that humans have done for centuries. In semiconductor foundries around the world, we take a large salami-shaped piece of silicon, we slice it into thin wafers, and then we do chemical reactions that remove some of it, that's the sculpting part, and then other reactions that turn parts of it into metal that'll connect the devices together, parts of it into insulators that'll separate those devices, and parts of it into the functional semiconductor by adding dopant atoms that'll control the properties of that material and allow us to have cell phones, computers, all the devices that we now live with around us. We in our laboratory expand the way that nanolithography is done, both from adding the bottom-up component, building synthetic elements together to make the structures that we want, and then my specialty is also really adding the chemical dimension to nanolithography, where in addition to having those controlled volumes of materials, we control the exposed chemistry. And what that lets us do is interact with the environment, whether that's biological, chemical, or physical.
When you talk about changing the chemistry functionality at the surface, are there other applications that these structures are useful for?
So we've been able to develop sensors to listen in on chemical signaling molecules in the brain as bugs talk to each other in the microbiome. We're able to listen in on how they're functioning, how they're able to tell each other what's going on. Ultimately, we hope to determine what a thought is and what a memory is through listening in on signaling molecules in the brain. There are abilities to control how electrons pass through these very thin layers by controlling where charge sits on them. And we can do that all often just with a single molecular layer.
So when you talked about listening in on bugs in the microbiome, when I hear microbiome, I think of the gut. And I'm wondering, are your devices one of the swallow the pill that is then able to sense things in the stomach?
Well, the gut is somewhat less accessible, if you catch what I mean, than other microbiomes. So in your mouth, for instance, you have 200 or 300 species. Some of them give you cavities. Some of them protect you from cavities. Some of them, if you have a periodontal implant, chew around that implant and it falls out. So it turns out periodontists and prosthodontists have no way to do reconnaissance of whether those particular species in your mouth or not. And so what we would like to do, we haven't done this yet, is listen in for the molecules that they emit and determine, do you have those harmful species? And if you do, then you would delay a surgery until you've cleaned your mouth out, if you'll pardon the term. And likewise for if you have the species that give you cavities, there are other species that exclude those, and those talk to each other through known signaling molecules. And so if we can develop these same measurement tools for those signaling molecules, we can learn about the health of your mouth and then guide treatment to avoid cavities, failed implants, and so forth. And so there are many microbiomes besides the gut that we can access more directly, for instance, in soil, in the ocean, in the atmosphere, the mouth, the vaginal microbiome, skin microbiome, and so forth.
So you mentioned these sensors in the brain. Can you talk a little bit more about how those probes work?
So those are actually an interesting hybrid. They've been developed for 20 years by Professor Ann Andrews, my colleague here at UCLA, and before that we were both at Penn State. Those are based on having a transistor, so essentially traditional semiconductor, although we use different materials than are used in your laptop. And instead of having a metal top with a voltage that controls whether electrons can pass through the semiconductor channel or not, we have DNA molecules that are specifically selected from very large libraries by our collaborator Milan Stojanovic and his group at Columbia University, so that they recognize the chemical signaling molecules, the neurotransmitters in the case of the brain, in other cases, other molecules, and they don't recognize related molecules such as the biological precursors and metabolites, so that as that DNA molecule recognizes the molecule to which it's sensitive, it changes conformation. Each DNA molecule has a single negative charge on each base, so that if you move that charge close to the semiconductor surface, you change the ability of electrons to flow through that channel and thus change the detected current going through that very thin semiconductor channel. And so in that way, we can detect the presence of the molecules that we're targeting, and we're insensitive to other molecules in the complex milieu, whether it's microbiome, brain, blood, or other mixtures.
So where do you see this technology having an impact in the future?
I think anywhere where chemical functionality matters, which is all of biology, much of the environment, there are opportunities for using this control of chemical functionality to advantage. And so what we do now is we look for where is an opportunity for us in another field, and with whom would we want to work to make that into a reality, and what would it take to take it all the way to being useful.
Well, I've very much enjoyed talking with you today. Do you have any closing thoughts that you want to share?
One of the amazing things here is we can reach smaller scales than anyone can reach otherwise in nanolithography. We can design hydrogen bonds between the functional part of the system that we have and the matrix down to 1/10 of an angstrom, and that'll determine the stability and structures that result. And with conventional nanolithography, we can't get down to those scales. And so really this adds a complementary tool to what exists in nanolithography, both from the semiconductor side and making devices and bringing those into the biological world on the one hand, but also in our chemical control and trying to place chemical functionality to match or simulate what might exist in a biological system.